Hello.
So I don't know if you can see me, but we are back in the office today. And I am hoping this works out today because like 3 minutes before the lecture started, all the lights went out. And I can't figure out how to get the lights back on. So I am going to be doing this lecture in the dark, which shouldn't change your experience, but a little spooky. Okay, so as we get started, before I get started, as always, I will ask if anybody has any questions they would like to ask. Okay, not hearing any. Can somebody give me a okie dokie if they can see the screen and hear me?
Yep. Yes.
Okay, thank you. All right, so we introduced this concept last time we met, last Thursday, and the concept was to use techniques to find the shear and moment equations for a given set of loading. So that for a given set of loading, you can find the equations for shear and moment, and then you can plot out and draw the shear and moment diagrams. So this whole lecture is really just going to be working through some examples of how to do that for different types of loading. So we're going to continue. As always, if anybody has any questions, feel free to ask or feel free to use the chat function as we're going through this. Okay, so let's start with example number 1. Please mention which section we cover each lecture. Okay, yeah, no problem. I think we are in section 6.1. I know we're chapter 6, and I don't think we've gotten out of section 6.1 just yet. But I can't be sure of that because my notebook and textbook are still in my home office and I am in my work office. So apologize for that. Okay, so example number 1 is a simply supported beam with a singular point load, as you can see on the screen. So it's not symmetric, as you can see. I have an 8-kip load 10 feet from the end on a 25-foot span. And what we want is find the equations for the shear and moment and plot the results. Plot your shear and moment diagrams. Okay, so the first step to all of these types of problems, the first step is going to be to find your reactions. To find your reactions, we're going to create a free body diagram. So in the free body diagram, the load is the load, but I have an unknown reaction at A and an unknown reaction here at B. I need to solve for those. So to find our reactions, we're going to sum our moments about point A equal to 0. So I have 8 kips times a moment arm of 10 feet, which is trying to turn the body in a clockwise direction. So I consider that to be positive. And we have an unknown reaction at B times a 25-foot lever arm that is tending to rotate the body counterclockwise. So that would be negative. Solving for my reaction at B, I have 3.2 kips and it is up. The reaction was positive. I assumed it was going up. It's positive, so it is going up. Then we sum the forces to equal 0. I have -8. I have plus 3.2, and I have plus, or I assume plus, my reaction at A equal to 0. And my reaction at A is 4.8 kips up. Okay, now that I have my reaction solved for, we need to decide on where and how many cuts we need to make. Okay, so I redraw the diagram. I put all my known reactions on here. So actually at this point now, all of the loading and reactions are known. How many cuts are we going to need?
2.
We are going to need 2 because I need 1 between the reaction and this point load is a discontinuity, and I need 1 between the point load and the other reaction. So I need 1 here, and I need 1 here. Any questions about why I chose these 2? Okay. So my cut number 1, I'm going to do a free body diagram of. Now, remember, cut number 1 is between the first reaction and the point load. So in cut number 1, you don't see any point load. There's no loading on this because the point load is on the other side of the cut. So I do draw my free body diagram. I put my known reaction on there at 4.8 kips. I have my shear drawn in the positive sense. I have my moment drawn in the positive sense. And the distance from the end to the cut is some unknown distance, x. Having set this up, now I can find shear and moment equations. If I sum my forces in the y direction equals 0, I have 4.8 up. I have my shear going down, so that's minus, all equal to 0. So therefore, my shear is equal to a positive 4.8 kips. I can sum my moments. I call this M1 because this is cut 1. So I'm finding the moment along cut number 1, so M1. Sum the moments are equal to 0. I have 4.8 times x, and I'm summing about the red dot right there. Always sum about the point on the cut to make this simpler. 4.8 times x tends to rotate clockwise, so it's positive. The applied moment tends to rotate the body counterclockwise, so it is negative. And so I find that m is equal to 4.8x, and this is measured in kip feet. This answer is valid between 0 and the point load, with the point load is located at 10 feet. So this shear and moment are only valid between the end reaction at 0 and 10 feet. Which means I need to do another cut. So this cut is going to be past the 10-foot point, and it's going to be between 10 and the right-hand reaction. And again, I draw my free body diagram. I put everything on there that I know. I put on my reaction. I put on the applied load. I have my shear drawn in a positive sense, my moment drawn in the positive sense. This is my cut number 2 at the red dot. And the distance from the end to the cut is, again, unknown x. Find shear and moment. Sum the forces equal to 0. I have 4.8 up. I have 8 kips going down. And I have my shear load V going down. All equal to 0. Therefore, V, my shear, is equal to minus 3.2 kips. Remember, there's no arrows on internal loads. You just have a positive or negative sense on your loading. Sum the moments equal to 0. I have 4.8 kips times x, tending to turn clockwise, so that's positive. I have 8 kips times, is not times 10 feet. The distance from the applied load to the cut is x minus 10 feet. So this distance here, I don't know what that distance is, but I know that it is whatever x is minus 10 feet. So 8 kips times x minus 10, and then that's tending to turn it counterclockwise, so that's negative. And the applied or the internal moment is trying to tend to turn it counterclockwise, so that is negative as well. And add all this up and simplify it, you get the moment is minus 3.2x plus 80 kip feet, and this is valid between 10 feet and 25 feet. Okay, so now we can draw the shear diagram. Between 0 and 10 feet, the shear is 4.8 kips. So there's 4.8 kips, and it is constant between 0 and 10 feet. From 10 to 25 feet, the shear is minus 3.2 kips, constant. So we draw it at minus 3.2 kips, constant. Any questions on the shear diagram? Okay, moment diagram. Between 0 and 10 feet, the moment diagram is 4.8x. Now 4.8x is the definition of a line. That's a linear equation. So if you think about it as y equals mx plus b, b is equal to 0. So when x is equal to 0, the moment is equal to 0. And there is 0 right there. When x is equal to 10 feet, which is to the distance of the point load, or the extreme of this range of validity, when x is equal to 10, 10 times 4.8 is 48. So at 0, moment is equal to 0. At 10, moment is equal to 48. Then we go on to this side. And again, I have the equation for a line. So if I plug in 10 feet into this equation, I have minus 32 plus 80 is again 48. This is a good check for you because there's no applied moment at this point. So there should be no discontinuity in the moment. Whatever you get for the moment at 10 feet from the left-hand side should equal the same number you get for the moment coming at it from the right-hand side. And you plug in 10 feet here, plug in 10 feet here, and you get the same answer, 48 kip feet. This is also why it is so important that x is always measured from the same point. If I didn't do that, then this x at 10 feet would not be the same as this x at 10 feet. So you have to be consistent. You have to run x from the same left-hand point every time. And then finally, if I plug 25 feet in for x, then I have 3.2 times 25 is going to be minus 80 plus 80 is equal to 0 again. That's your other check. When you're drawing moment diagrams, if the original problem has no applied moments at the ends, and there's no possibility of restraint for moments, no fixity at the ends, then the moment diagram has to equal 0 at the ends. So when you plug in the values that you got, 0 here, 25 here, you better end up with 0 at those ends, or there's something wrong. Okay, do I have any questions about example number 1?
Professor,
Yes.
so we get parabolas only with uniform loading, right?
You get a parabolic moment diagram when you have a uniform load. That is correct.
If there was an applied moment, is there like a step in the moment diagram?
Yes, there is. Yes, that's exactly right. And I do have an example that will show that to you in a couple of examples. Any other questions for example 1? Okay. Example number 2. Oh, there's the applied moment. Okay, so it's the very next example. So this beam has only an applied moment to it. There are no vertical loads to it. So it's simply supported. It has an applied moment going in the clockwise direction at 12 feet. The total span is 30 feet. We want the shear moment diagrams and equations and diagrams for this example. Okay, so where do we start? I kind of gave it away, didn't I? Where do we start?
Find the reaction forces.
Got to find our reactions. Absolutely. So to find our reactions, we draw a free body diagram. Okay, this is not a free body diagram. This one is, where I have all of my loading and all of my restraints labeled on the diagram. So I draw my free body diagram. I have an unknown reaction at A, an unknown reaction at B. Now we can find our reactions by summing our moments about A. Okay, when I sum my moments, a clockwise moment is positive by my reckoning. So there's your positive 600 kip feet. And my wife just texted me. She forgot I'm in the middle of a lecture. I will get back to her later. Okay. Notice though that your 600 foot moment, there's no, this 12 feet does not come into this equation. 12 is not in this equation at all. And the reason why is when you're summing moments about a free body, it doesn't matter where the 600 kip feet is applied. Isn't that kind of strange? It doesn't make any difference at all on how this body wants to rotate if that is applied at 12 feet or at the end or at the other end. It doesn't matter. It's just a twisting action anywhere on this body is 600 kip feet. So you do not have 600 times 12 or anything like that. The 600 is the moment and it is clockwise. So you just put it as a positive moment. And if you check your units, you'll see that this is true because the 600 kip feet matches the units of a reaction, which is kips times feet. So this is the only way it works. So I put my 600 kip feet in there as a positive moment. And then I have my unknown reaction B trying to turn the body counterclockwise. So it's negative times a 30-foot lever arm. If I solve for that, my reaction at B is 20 kips and is positive. So it's in the direction I assumed, which is up. Any questions about that? Okay, then we sum our forces into Y. And the only forces I have in the Y is my unknown reaction at A, which I assume going up, and my reaction at B, which I know is going up. So they're both positive. Therefore, my reaction at A is minus 20 kips. It's actually down. It's holding that end of the beam down. Okay, so now that I have my reactions, I draw my diagram and I put everything on there just like I know it. A is down, B is up, and my 600 kip foot applied moment. How many cut points do I need?
2.
I need 2. But I want everybody to understand why I need 2. I need 2 because this reaction is a discontinuity, so that's one discontinuity. This applied loading is another discontinuity, so I need a cut between them. And between this discontinuity and my other reaction, which is a discontinuity, I need another cut. So in between any discontinuity requires another cut. So I need cut number 1, I need cut number 2. Does that make sense? To anybody?
Yes.
Yes.
Okay. So free body diagram for cut number 1. This is the cut that is to the left of the applied moment. I have my reaction on there drawn in the correct direction. I have my positive shear, my positive moment, and there's nothing else on this. The distance from the reaction to the cut is my unknown x. Find the shear and moment. So if I sum the forces in the y equal to 0, I have minus 20 minus v equals 0. So my shear is equal to minus 20 kips. It's actually a negative shear, which is fine. If I sum my moments about the red dot there, I have minus 20 kips times x. And this is minus because it's tending to turn the body counterclockwise. Not necessarily because I found this to be negative, but more importantly, the direction of the 20 kips is turning the body counterclockwise. That's why it's negative. 20 kips times x. The internal moment, a positive moment, is trying to turn it counterclockwise, so it's negative as well. Solving, m is equal to minus 20x, and this is in kip feet. This answer is valid between 0 and 12 feet, which is where the applied moment is. Free body diagram for cut number 2. Now I'm on the right-hand side of the applied moment. So I have my reaction at A, my applied load, positive shear, positive moment, x distance from my end reaction. Find the shear and moment. Sum the forces in the y equal to 0. I have minus 20 minus the shear. The shear is still equal to minus 20 kips. Isn't that interesting? So apparently this applied moment does nothing to the shear. And that is the case. If I sum my moments about the red dot, I have minus 20 times x. Same reason as I just explained why that's negative. The applied load is tending to turn the body in a clockwise fashion. It is positive. The internal moment is trying to turn it counterclockwise. It is negative. And notice I'm being very careful to describe why this is negative, why this is positive, why this is negative. It's important to get those points right. Solving, my moment is equal to minus 20x plus 600, and the units are kip feet. This answer is valid between 12 and 30 feet. If I draw the shear diagram, the shear from 0 to 12 feet is minus 20 kips, and from 12 to 30 feet is minus 20 kips. So the shear diagram is just a constant minus 20 kips for the whole span. Now the moment diagram, a little different. The equation for the moment from 0 to 12 is minus 20x. Again, that's a line. So you can plug in 0 and you get 0. You can plug in 12 into minus 20x and you get minus 240 kip feet. So that is the first part of this equation is dictated by this equation here. Now for the second part. If I plug in 12 into x here, then minus 220 times 12 plus 600 gives me a positive 360. So here, there very much is a discontinuity. There's a big step in the internal moment because of this applied moment. And if you notice, 360 plus 240 is 600. So the applied moment was a positive 600 kip feet. The internal moment jumped up 600 kip feet. And then finally, if I plug in 30 feet into here, then minus 600 plus 600 is equal to 0. Just as I said before, if there's no fixity at the end of the beam and there's no applied moments at the end of the beam, then you had better get 0 and 0 for the end moments on that beam. I also mentioned at the beginning, does it make no difference where the applied moment is applied at 12 feet or 20 feet or whatever? Well, here it does. If the applied moment was over here, then the shape would be completely different. So yes, it does matter where it's applied, but it doesn't matter to the shear diagram where it is applied.
Professor,
Yes.
so the moment diagram tells us the moment at anywhere along the beam.
Yes.
So what would actually be the moment at x equals 12 feet? Is it negative 240 kip feet or is it 360 kip feet?
Yes.
Thank you.
It is considered like one of those mathematical singularities. So at exactly 12 feet, it is either minus 240 or it is 360. It is both. But the better way to think about it is at 11.999 feet, it is minus 240. At 12.001 feet, it is 360. But mathematically, it's one of those singularities, right? So at that exact point, it is actually either, depending on
Okay.
which direction you came from.
All right,
That
thanks.
was a good question. Any other questions on example 2?
Professor, like, how you deal with these kind of problems in reality? Like, you count it as negative 240 or?
Oh, all right. Well, no, that's a great question. So in reality, the beam at this 12-foot point, the beam could be like a steel beam. I don't know if you can see me, but a steel beam is symmetrical. So the top flange and the bottom flange are equal and equal distance from the center. So a steel beam is equally strong from negative bending or from positive bending. So if the bottom flange is in tension or the top flange is in tension, doesn't make any difference. It's the same strength. So if it was a steel beam, then I would just look at the greater of the two. I would say, okay, well, just to the right of this 12-foot mark, the moment is 360. 360 is a more severe loading than 240. I'm going to design my beam to handle the 360. But if it's a concrete beam, totally different philosophy. Because a concrete beam,
Tension and compression.
yes. So the positive moment, the 360, causes tension on the bottom, compression on the top. So I would have to size my rebar, which takes the tension on the bottom for the 360. But the minus 240 puts tension on the top and compression on the bottom. So I would have to design my rebar at the top of the beam for the 240. So I would have one design for rebar at the bottom based on 360 and another design for rebar on the top for the minus 240. And then of course, when you build the beam, you would have rebar on the bottom and the top. The top sized for the 240, the bottom sized for the 360. Yes, so that's exactly why this is so important, that when you get to your design classes, if you did just the slightest little foobar, can I say foobar? I said foobar. If you'd make the slightest little mistake and you put a positive instead of a negative, you will end up with a moment diagram that has 240 on the top, 360 on the bottom. And you're thinking to yourself, it's just, what's the difference? I got the numbers right. Well, if you got the wrong rebar on the top or on the bottom, you have a catastrophic failure. That's what you have. It's very, very important to keep the positive and the negative moments straight, and that your moment diagram accurately reflects where the negative moment is, where the positive moment is. It makes a big difference when it comes to your material design. Good questions. Anybody else? For example, number 2. Okay. Let's move to example number 3. Find equations for shear and moment, plot the results for a cantilever beam. So here we are a little different. This is not a simply supported beam. This is a fixed support for a cantilever beam. The length is 15 feet. I have a point load pushing down of 50 kips. I have an applied moment at the end of minus counterclockwise 300 kip feet. Okay, so what's the first step? What do we always do first?
Find reactions.
Find reactions. Thank you. So here's my free body diagram. I have my applied loading, and I have my assumed reactions. Now, I say assumed because I put my reaction of the moment at A as clockwise, and I put my reaction of the vertical at A as up. Those are my best guesses, but they may or may not be right, and that's totally fine. But you have to assume something. So draw what you assumed, and then if you get a negative on something, then it's the opposite. So now that I have my assumed reactions and my applied loading, let's find our reactions. We're going to sum our moments about A equal to 0. And summing moments, I have this 300 that is tending to turn the body counterclockwise, so it's negative. Again, it doesn't matter where the 300 is applied. There's no moment arm, if you will, because this is already a moment. Then I have the 50 kips, which does have a moment arm because this is a vertical load times 15 feet, and it's tending to turn it clockwise, so that is positive, plus my end reaction MA. The way that I drew it is trying to turn the body clockwise, so it's positive as well. And when I solve for MA, I get a minus 450 kip feet. So my assumed direction was incorrect. I have to put my arrow here. All reactions have to have an arrow. My arrow is indicating that it is actually the other direction. Now I sum my forces in the Y equal to 0. I have a positive reaction at A. I have minus 50 kips equal to 0. So my reaction at A is 50 kips positive. So therefore it's up. Now we need to decide on our cut points. Here's my illustration showing all of my applied loading and showing all of my reactions. When I do my, pardon me for a second, my computer's barking at me. Okay. Sorry about that. I'm running dual systems. My other computer just yelled at me. Okay. So remember, this was minus. So now that I know that the direction is counterclockwise, I put it as counterclockwise. This one, I know the direction is up, so I put it as up. Don't put minus 450 here. You just hopelessly confuse yourself. Just put the magnitude and the direction that you found from this step here. Okay, does that make sense to everybody?
Yes.
Okay, so how many cuts do I need?
I think one.
Yes, I only need one because there is only, these two discrepancies are at the same point. These two these discontinuities at the same point. These two discontinuities are at the same point. So I only need one cut to fully describe everything that happens between those 2 points. So we do a free body diagram. I'm looking at everything on the left. I'm not looking at anything on the right. On the left, I have my 450. I have my 50, positive shear, positive moment at an X distance from the end. Sum the forces in the Y equal to 0. I have 50 going up. I have my shear V going down, so it's negative, and my shear is equal to 50 kips. Sum the moments. I have 50 times X, that's trying to turn it clockwise, so that's positive. I have minus 450, that is counterclockwise, that's negative, minus, or I got M, that's also turning counterclockwise, so it's minus. So solve for M. M is equal to 50x minus 450, and this is kip feet. This answer is valid between 0 and 15 feet, which is the whole span. So my shear diagram, I have a constant 50 kips. So anywhere along the span, it's 50 kips. So I just draw a constant 50 kips. For the moment diagram, this is again the equation for a line. You can recognize this to be linear. And to solve for that line, you can either do y equals mx plus b, solve for b, and solve for m. Nothing wrong with that at all. That's one way to solve it. The other way to solve it, which I think in cases like this might be simpler, is the plug and chug. So you know it's going to be the equation of a line. You know that it's going up because m is positive. But to really get the points, all you need to do is just find out what is it at 0. So you take 0, put it in here, and you get minus 450. What is it at 15? Take 15 into here. So 50 times 15 minus 450 is equal to 300. And there it is. That's your moment diagram. Now, does the moment diagram make sense? Well, I have a moment here at the end. And remember what I just said, the ends have to be 0, remember? Well, the ends have to be 0 unless you have an applied moment or a reaction at the end. Then it's not going to be equal to 0, but it's going to be equal to either that reaction or the applied load. So my moment at the end is equal to my end reaction, and the moment at the other end is equal to the applied load. So that's how you know those are okay. We would also want to be able to find, where is this inflection point? Where does the moment go from negative to positive? And to solve for that, you use similar triangles. So you can say that the whole span is 15 feet, and the total moment is 450 plus 300 is 750. So you have 15 over 750 is equal to x over 450, similar triangles. Then you just solve for x. X is equal to 9 feet. And we're gonna use where is the inflection point a bit later in several different ways.
Professor, can you go back really quick?
Sure.
Is it okay if we just set the equation equal to 0?
The 50x minus 450 equal to 0 and solve for x?
Yeah, because I've never done, well, it's not like a harder method, but I'm just used to the setting equal to 0 part.
You absolutely may.
Okay.
You absolutely may. And I think one of the last examples that we do, you have to, because they're not triangles anymore. So yes, for everybody else, what she is basically saying is that this equation right here, you can set that equal to 0 and solve for x, because somewhere on here, this equals 0, solve for x, and you'll get the same result, x equals 9 feet. Oh, my coworker just said you have to spin the timer to turn it back on. Lights go out at 5:30. Why would the lights go out at 5:30? It is by the exit door AC controller on the wall. I am not texting my friends. Found that, but did not turn on my lights in offices. All right. So many distractions, you know? I was better off at home. Okay, everybody ready for example number 4?
Yep.
Okay, we are going to find equations for shear and moment and plot our results for a beam with an overhanging cantilever. So in this case, what this is illustrating is, this illustration was one of the earlier lectures that I had started last spring. So you notice that my quality of my illustrations has somewhat degraded. We'll get back up there, but this is the PowerPoint method of creating illustrations. So sorry about that, but what this is meant to illustrate is a 5 kip load, 5 kips per foot applied over the entire 40 feet of the beam. And there's a 20 kip load right on the end of the cantilever. We need to find our reactions. So we're going to create a free body diagram. I have drawn the diagram. I've got my unknown at A, my unknown at B, my 20 kip load at the end of the cantilever, but I can't work with this 5 kips per lineal foot in summing my forces. I need a resultant. So the resultant is going to be 5 kips times the whole 40 feet is equal to 200 kips. So the resultant of this uniform load is a 200 kip point load applied at 20 feet, which is half of the 40. Okay, is everybody cool with that?
Yep.
Yeah.
Okay. So now we can find our reactions. Some are moments about A. I have 200 kips times 20 feet, turning it clockwise, so that's positive. I have my unknown reaction at B times 30 feet, turning it counterclockwise, so it's negative, plus my 20 kips times 40 feet, clockwise, positive. and my reaction at B is 160 kips, and the assumed positive is correct. Sum our forces in the Y equal to 0. I have a positive RA minus 200 minus 20 plus 160 all equal to 0. So my reaction at A is 60 kips positive, so it's up as assumed. So there's my reactions. Now we need to check on our cut points. And so I redraw the diagram again with all the loads that I know that are there and all the reactions that I know that are there. Here's an important point. When I redrew this diagram, I did not redraw it with the resultant. I didn't put a 200 kip point load here. And if I had, then I would have gotten the wrong number of cuts, and each cut would have had the wrong summation of forces. If I put my resultant here, then I would have done a cut here, here, and here. That would have been totally wrong. So I can't reiterate this enough. You have to understand that this resultant is only good for finding your global reactions, and that's it. After you found your reactions, dump this thing. Don't go back to it. Go back to the real loading. Now, with the real loading, how many cuts do I need?
2.
Just 2. I need one here. I need one there. Yep. Okay, so let's do a free body diagram for cut number 1. I have my 60 kip reaction. I have my 5 kips per lineal foot. Again, I have to keep this as a uniform until I get to summing forces on that free body diagram. Positive shear, positive moment. Sum the forces in the vertical. I have 60 kips up. I have my 5 kips per lineal foot times X pushing down, so that's negative, minus my shear is negative. So my shear, if I solve for V over here, I get minus 5X plus 60, and the units are kips. So yes, a uniform load produces a linear shear. Sum our moments. I have 60 kips times X, and clockwise, positive. I have 5 kips per foot times X is the force times X over 2 is the moment arm. Counterclockwise, negative, and then the moment is counterclockwise, so it's negative. Okay, so everybody catch what I did right here? The 5 times X is the resultant located at X over 2 from the red dot. So 5X times X over 2.
Yeah, we got it.
Okay. Solving, I have my moment is equal to minus 2.5 X squared. That's this dude here. Plus 60X is this half over here. And my units are kip feet. This cut is valid, or these equations are valid from 0 to 30 feet. Now we need cut number 2. And here is where I said before, you always take X from the left-hand side. Even though it's closer and simpler to take it from the right-hand side, you would have the wrong X, you would have the wrong answer. X is always taken from the same reference point. So I have now 60 kips, and I have 160 kips at 30 feet away. I have the distance from 60 is X. The distance from 160 is X minus 30. We don't know where X is, so we can't define it any better than just that this distance is X minus 30 feet. I have 5 kips per lineal foot over the whole span, and I have positive shear, positive moment. Guys starting to pick up on the patterns? They really are, no matter how ugly or complicated or nasty I can dream these things up for your exams. Ha ha ha. It's always the same process. So I am going through these problems from simpler to more complex, but you should be picking up on the patterns. No matter how many cuts you need, every cut is done the same way. Okay, so the pattern. Solve for your forces in the y. I have positive 60, positive 160, minus my 5 kips per lineal foot times x feet minus v equals 0. So solving this, v is equal to minus 5x plus 200. Uniform load produced a linear shear. So summing the moments about the red dot, I have 60 times x clockwise. I have 160 times x minus 30 clockwise. I have 5 times x times a moment arm of x over 2, and it's turning counterclockwise, so it's negative, minus my positive moment because it's turning counterclockwise, so negative. Some,
Professor.
yes.
Oh,
I
someone
was
can.
gonna say. Oh, you wanna go?
No.
Oh, okay, no. Okay, so I think the shear here should it be negative 5x plus 220?
That certainly looks like it, doesn't it? Yeah, looks like I got a typo. The way I have this set up, I don't know what, I'll find it later. But yes, no, you're right. And that 220 is right there. So yeah, that was a typo. Okay, who else had a question?
Oh, I was just saying the same thing. You beat me to it.
Oh, you guys are so smart. Okay. So yes, for everybody else, that 200 right there should be a 220. And got that, okay. So this equation is now, this is valid from 30 to 40 feet. And this is equation. So, and the load is uniform. So the shear is linear. The moment is parabolic. All right, so now we need to draw the shear diagram. This looks kind of complicated and nasty, maybe, but it really isn't. All you have to do to draw this is look at the extremes of your ranges here. The shear is linear, the shear is linear. So all you need to do is plug in 0 and you get 60 here. Plug in 30 into here and you get minus 90 kips. Down here, plug in 30 here and you get 70. Excuse me. So if I take 30, plug it in here, I get 70. It's not the same number, but if you notice that it's jumped up by 160, the reaction has jumped the shear diagram up by 160. So this is actually correct, minus 90 to 70. And then if I plug in 40 into here, then I should have 20, which again, that's supposed to be 220. So 40 times minus 5 is minus 200 plus 220 gives you 20 kips. And the 20 kips is correct because the very last thing that happens is I have a 20 kip load that pushes this back to 0. Okay, but the point being at this stage of the game is if everything is linear, really all you need is the beginning and the end for each segment. So plug in 0, plug in 30, plug in 30, plug in 40, 60, minus 90, 70, 20. And that's your shear diagram. Any questions on the shear diagram? Okay. And this time, we need to find where this inflection point is so that we can plot the moment diagram. It'd be very difficult to plot the moment diagram without knowing where this inflection point is. So to find the inflection point, again, I turn to similar triangles. You could solve this equation here equal to 0, and it will give you exactly the same thing. So you could set this equal to 0 because that's this equation here, or recognize that x over 60 is equal to the whole 30 feet from here to here over 60 plus 90. And that gives you x is equal to 12 feet. That's where the shear equals exactly 0 at 12 feet. Now the moment diagram. And I know that when you guys do this, you're not going to have this shape kind of just jump out at you like this. But we can work through this. Okay, so to find the inflection point for the moment diagram, we will have to solve for where the moment is equal to 0. Clearly to the left, the moment is positive. Clearly to the right, the moment is negative. So somewhere along this span, the moment's going to equal 0. To do so, I take the equation for the moment between 0 and 30, and I set it equal to 0. I solve for x. I get x is equal to 24 feet. So we can find the maximum positive moment by, first we could take the first derivative and find x2. So the moment, again, what I'm doing is between 0 and 30 feet, the moment is described by this equation. So I can take the first derivative of this equation, which is minus 5x plus 60, set that equal to 0, and I get 12 feet, which is exactly the same result we just got by finding the inflection point of the shear. Where the shear equals 0 is where the moment diagram equals a maximum at 12 feet. So now I can find the maximum moment of 360 kip feet by taking 12 and plugging it back into my equation. So minus 2.5 times 12 squared plus 60 times 12 is equal to 360. Okay, everybody following? Anybody not following? Did I lose anybody?
Yeah, you kind of lost it on that last part.
Okay, which part?
Just how you got the 360.
Okay, so let's do it this way. Let's go back up here. Okay, see where the shear is equal to 0? And I got 12 feet. You're okay with getting that 12 feet from the shear equals 0?
Yes.
Okay, then let's go down here. Forget that, forget that. And what I did is I took that 12 feet that I found from where the shear equals 0, and I stuck it right there for x. And I solved for the moment. The moment's equal to 360.
Okay, thank you.
Yeah, no problem. So then what I did is I said, instead of finding where the shear is equal to 0, if you weren't sure that that is where the maximum moment is, then what I said was we can recognize, and I'll explain this just a little bit, we can recognize that where this is at its maximum, the slope on that has to be equal to 0. So I took the equation and I took the first derivative, which is the equation for the slope. and I solved for where the slope is equal to 0, and I got the same point, 12 feet. Okay, does that make sense?
Yes, thank you.
Okay. All right, and now what about this point over here? How do I figure out what that moment is equal to?
Is it negative 450?
Because I know its location. I know that this is located at 30 feet, x equal 30. So I can take x equal to 30 and plug it straight into this equation, and I'll get minus 450 kip feet. I can also, in fact, I should take 30 and plug it into the equation for this side of the line between 30 and 40 feet, and I should get exactly the same answer because there's no jump here. There's no applied moment. So there's no way that this can have a bump right here. So that's another way to check yourself. The equation for the moment, let's go back up here a second. The equation for the moment here, if I plug in 30 into this x, I get minus 450. But this equation here, if I plug in the same 30 feet, I had better get the same answer, minus 450. And I do. Minus 450. And then that second equation, if I plug in 40 feet, then I had better get 0 because this end has to be equal to 0. That's the free end of the cantilever. There was no applied moments and no means of rotational restraint. So this has to equal 0. Okay, that was the end of that example. Any questions on example 4? We got one more to go.
So in diagram, you need to show what's the maximum moment and the minimum moment, and then for shear, it's the same thing, right? That's
Yes,
what
it
you need
is.
to show. Okay.
Yes, yes. That was a great question. Forgive me. I didn't even say that at all. Thank you. Yes, for these shear and moment diagrams, you have to label all these points. Wherever there's a discontinuity is where you need a point label. So here, here, here. Now this guy right here, clearly this is not a maximum or a minimum. The minimum is here, the maximum is here. But you need a label here because there's a discontinuity. So anywhere that the flow of the line is interrupted, the beginning and the end of every segment, if you will, needs a label. Yes, thank you for that question. I just totally blew over that. Here, the maximum and the minimums have a label. Really, to be complete, I should have a 0 here and a 0 here as well. And then generally speaking, you also want to identify where this inflection point is. Where does it go from positive to negative? That should be identified as 24 feet. Okay, example 5. Anybody not ready for example 5?
I had a question regarding the last example, if that's okay.
Sure, of course it is.
Could you explain the last part of the graph where it goes from 30 to 40? Like, why is it drawn that way, concave up or down? Or is
Okay,
that something I can worry about later?
both. We're going to worry about it now, and we're going to worry about it later. Yes, no, that's a good question. Okay, so this portion of the graph is described by this equation right here. And I just realized, see that little 2 right there? That's clearly a typo. That's supposed to be a squared, you know, like that one. So please don't think that I came up with x2 from somewhere. It's not the roller coaster. That's supposed to be x squared. So this equation describes the moment diagram from here to here. And if you were to take this equation, it's a negative parabola or a negative quadratic. If you plot that equation between the points x equals 30 and x equals 40, you will get the shape that looks like what I drew, more or less. And let's see, this would be the concave. I don't know, convex, concave, but the way that I drew it here is the right path. And if you drew it the other way, if you drew it this way, that is incorrect. And so how would you, the student, know that? So the green is correct, the red is incorrect. So a very absolutely valid question. How would you even know which is the correct way to do it? Well, if you plot the equation like on a graphing calculator or MATLAB or something to that effect, that would tell you the right one. If you plugged in 35, the midway point, and found what the moment is at 35, that would tell you. Or just plug in a couple points and that would tell you. Depending on how far we get tonight, next lecture, we're going to talk about how to do this the graphical way. And I will talk about more theory about the relationship between shear and moment that would also tell you how to check which way is right, which way is not. Okay? That's a good observation for now. How would you know this? At this point in the game, before we get to next lecture, at this point in the game, you would only know by either plotting that equation or solving for a couple points in here and basically manually finding out, is it convex or concave?
Professor, isn't before like, because we have like negative x squared, so we have to get like negative parabola
Yes.
for all the graphics?
Yeah, and that's what Peter just said too. Or you can see the equation is parabolic with a negative in front of the x squared, showing that it would be a graph concave down. Yes, no, you're both right. You're both right. It's just that it's not always obvious. So I want to give you more tools in case it's not obvious like that. Okay, you know what? I don't think we should rush through the last example. The last example is actually one of the more complicated ones. So what do you guys think? Let's just save the last example. We'll glob it on to the beginning of the next lecture and we'll take more time with it. It's always better to have the time to go through it properly than to just rush stuff through, because that doesn't help anybody if you don't, go so fast, you don't know what I'm talking about. So what do you think?
I think we should save it.
All right, then we shall save example 5. Let me write that down. And we'll start next lecture with that on Thursday. And so, does anybody have any other questions they would like to ask now? We still have 6 minutes, 6 quality minutes.
I have a question for the homework.
Sure.
The 6.50, 58, and the 70, the last 3. So you only want the figure of that one. So we don't answer the question of the actual problem.
Yes, that's right. The actual problem, if these are the ones I'm thinking of, the actual problem is saying find the center of gravity and the moment of inertia, and then due to the applied moment shown in the diagram, solve for the induced stress or something to that effect. And I don't want you to do all that. I just want you to find where the center of gravity is and the correct moment of inertia.
Oh, okay.
Does that make sense?
Yeah.
Because otherwise, I couldn't ask those homework problems until about another 2 or 3 lectures down the road when we talk about the flexural formula. And by the time we get to there, the lecture that I did on section properties is like way in the past. I wanted to hit you guys and get you to practice moment of inertia and center of gravity while it was somewhat fresh from the lecture that we did on that.
Okay, thank you.
Okay. Any other questions? All righty, then we will stop the recording and everybody have a great night. We will pick this up on Thursday.